Physics is one of the most fascinating subjects that humankind has ever researched. The realization of its complexity not only inspired brilliant minds but also established mind-blowing theories over the course of history. Einstein's theory of relativity is one of those concepts that appeared ambiguous even to the physics community. Even now, many students seem to be confused by it. So what is Einstein's theory of special relativity?
Prior to the 1900s, the nature of space and time was considered to be absolute, meaning that all observers saw the exact same thing. It was thought that light travelled through a medium that filled empty space called the luminiferous ether. It was assumed that the speed of light depended on the motion of the observer relative to that of the ether, similar to other waves that we had observed. The ether concept was thrown into doubt when an experiment by Albert Michelson and Edward Morley to show that there was a wavelength change caused by the ether failed to show any evidence of this. This theory was clearly incorrect and a new one was required. In comes Albert Einstein in the early 20th century with his new theory of relativity. He postulated that there was no ether, but that light had a constant speed in all inertial frames, and thus travels at 300,000 km per second relative to an observer regardless of their velocity. Using the work of the Dutch physicist Hendrik Lorentz, Einstein proposed his theory of special relativity. Included in this was time dilation.
Special relativity suggests and experimentally confirmed that the faster an object moves through space, the slower it moves through time. Consider two people running. If runner A moves with a speed of 10 meters per second and runner B with 25 meters per second relative to the stationary observer watching from a distance, then the speed of runner B from the point of view of runner A is only 15 meters per second. This suggests that velocity is relative, and hence so is time, in order for the speed of light c to be constant. Thus, time passes at different rates for the two observers. This is called time dilation. The closer the speed of the moving object is to the speed of light, though, the more noticeable the effect is. The equation describing the above phenomenon is where v is the speed of the moving object, in our case the runner. C is the speed of light, T0 is the time measured by the moving object, and T is the time measured by the external observer. From this equation, we can see that the larger the velocity is, closer to the speed of light, then the smaller the denominator is, and hence the larger the time t recorded by the external observer. This therefore suggests that according to the stationary observer, the time of the moving object passes at a slower rate. Therefore, time dilation has been achieved.
Before Einstein, it was assumed that length is a fixed quantity, irrespective of how the object moves or travels. According to the Lorentz transformations required by Einstein's postulates, this is in fact incorrect. Einstein said that time is relative and that the length of an object is relative. He said that when an object approaches the speed of light, the measurement of space changes, leading to objects being perceived as smaller. This process is known as length contraction. For example, if two objects are moving far away towards a planet, in one we see it from a perspective of a person on Earth, with the Earth as the inertial reference frame, and in the other we see it as a person on the aircraft itself. The person from Earth will see the object moving at some certain constant velocity v, and will measure some distance LO, known as the proper length, as this length is measured by the observer at rest with respect to the start and end points, which is the person on the spacecraft. However, on the aircraft, the only thing in common is the relative velocity v, and in this case it represents the velocity of the Earth and the destination as they move relative to the aircraft. The velocity must be the same for both, so everything else, i.e. the other properties, must be different. These are time dilation, and the two objects will arrive at different lengths of journey, the contracted length L, and with different lengths of the aircraft, as this dimension is parallel to the direction of travel. The earthbound observer would see the aircraft as much shorter than the astronaut does. So there's a formula for length contraction where we can actually relate the proper length and the contracted length, and this is given by And now, as a real life example, for a muon has a half-life of 1/1000th of a second at rest, but stationary observers would see a longer decay time due to the relativistic effect.
And that's all for today. Thanks for watching our video. See you next time.